Welcome back. In this particular video on linear regression, I'm going to talk about automatic variable selection. So till now in our linear regression series, we've covered a variety of topics. So we've covered in our previous lecture, we just covered one-hot encoding or binary coding to bring in categorical variables into a regression model. And before that, we had covered how to check for multicollinearity using variance inflation factor. And before that, we had covered the assumptions of OLS regression, how the three assumptions need to be checked, that dependent and independent variables have a linear relationship, that the independent variables do not have a relationship between themselves, and finally that the residual should be IID with a mean of 0 and a normal distribution, and should have homoscedasticity. So that's covered in IID itself, and we will do residual analysis later on. In this particular lecture, I'm going to talk about automatic variable selection. So what do we mean by automatic variable selection? So in our previous video, I demonstrated how we built a model on the HSB2 dataset, and how at each step in time, after checking for collinearity, when I wanted to include only significant variables in my model, so I started with all the variables in the model that we have. So I've started out with science, read, write, social studies, and all the three race categories that I had created using one-hot encoding. And then I started removing the variables one at a time. So I removed race underscore H or Hispanic first of all, because it was the most insignificant. Then I removed African American, and then finally I removed social studies. And then this was the final model that we had. Then I tried putting in gender also, and then we removed gender because it was an insignificant variable. Now what we can actually do is we can actually automate this procedure to a certain extent. By automation, what we mean is we can ask SAS to do these cycles of bringing in variables or pulling out variables from the model. And in SAS, there are a variety of methods to actually force automatic variable selection. And this is most helpful when you are dealing with the dozens and dozens of independent variables. So if you have only a few independent variables, it's uh, it's uh, it's suggested that you do it by hand, like I demonstrated in the previous video. So you manually look at the parameter estimates, then you look at the p-values, and then start adding and removing. But that can become cumbersome if you have like 50, 100, or maybe 1,000 independent variables. And 1,000 plus independent variables is not an unknown thing when we do modeling. And when we are talking about so many independent variables, it can become difficult to do this manually. So there are some procedures which can automate it. And the three types of techniques which I'm going to cover today are forward selection, backward selection, and stepwise selection. So let's talk about forward selection first of all. So what we do in forward selection, so I'll demonstrate it graphically. So let's say we are doing forward selection, and this is a model that we want to build using the variables, and this is the uh, this is the pool of variables that we have. So we have variables x1, x2, x3, all the way till xn in our model. So in the initial model or step 1, I start with only the intercept, and which is basically the mean value of my dependent variable without any variable in the model yet. So in the first model, first step, I have only the intercept and no variable in the model. Then what do I do is I look at each of these variables and calculate the p-value of them p-value separately, i.e. what is the parameter estimate against each value or each variable separately. So I calculate the beta naught for beta 1 for each of them separately. For x2 it will be beta 2, for x3 it will be beta 3, and so on. I calculate all the beta n separately, and I look at the t value, or I perform a t test against this beta estimate, and check whether this beta estimate is actually coming from a population of 0 or not. So I get a t value which converts into a p value. So I get the p values for each of these estimates over here, and then I will select the variable which is the most powerful predictor. How do I do that? So you're looking at the p values, you can sort it in descending order, select the p value which is the smallest, you sort it in ascending order and select the p-value which comes up at top. So that variable with the smallest p-value is the variable which has the highest t-value effectively, and that variable has the strongest linear relationship, and we bring that variable into our model. So step one, we have the first variable which comes in, let's say x3 comes in, so my model has only one variable x3. In step 2, I again recalculate and check the estimates against each of these variables and bring in one more variable. So let's say x3, and then I bring in x3 and x5. In the third step, I bring in another variable, let's say x3, x5, and let's say 10. And I keep doing this procedure. So I keep repeating this ad nauseum till the time there are no more variables in my pool left which are significant to bring in. So I end up with a subset of variables from my overall pool, and this is my final model. So this becomes my final model. So what we've done is we've automated the step of bringing in one variable at a time from my pool of available variables, and we will stop only when amongst the pool there is no variable which has p-value less than alpha, and we can set this alpha at whatever level. So I can set the alpha at 0.05, or I can set it at 0.10 or 0.15. We rarely go above 0.15 in regression, and in most cases 0.05 should suffice for our modeling. So in cases where we don't get a very high R square, we might relax the value of alpha from 0.05 to 0.10, maximum till 0.15. We rarely go beyond 0.15 because those variables, even if you do bring them in, they're not likely to have any meaningful impact in explaining the variance of the dependent variable. So in forward selection, we add one variable at a time. Till there are no variable left with the p-values less than alpha to bring in, and the final model that we end up with is the set of variables from my pool. So essentially I could start off with a pool of 1000 plus variables hypothetically, and do this automatic forward selection procedure and end up with a subset, let's say 50 to 60 significant variables only. So if I had to do it manually, I'd have to look at the parameter estimates in my output model with for all 1000 variables and manually start reading out or bringing in variables, and that would be a lot of effort. So if you're starting off with only 10 or 12 variables, you might do it manually, but more than that, it helps in exploring the hypothetical regression models using automatic selection. So this was forward selection. And let's quickly recap, what does forward selection do as per the PPT. So modeling starts with only the intercept, and then the variables are added one by one. So each time we add the variable, we look at the full model, we look at the R square, etc. And we continue adding variables till there are no more significant variables left to be included. The significance level that we use needs to be set by the analyst himself or herself, and I'll show you how we can set that. So that was using forward variable selection. Now the exact opposite is backward variable selection. So how does backward variable selection work? So backward selection will be the exact opposite. So I start off, so let's say I have the same model iterations that I have to do. I start off with the pool of variables. So I have a lot of variables, x1 till xn. Let me make it an x, and this is also an xn. Alright, so in my first step, I will include all variables in my model. So it will have all variables in the pool, and then in the second step, I will remove the most insignificant variable. So remove the most insignificant variable. So now I have, in the second step, I have all variables minus 1. So I have removed one variable which is the most insignificant, and the variable which is most insignificant I can visually identify by looking at the p-values. So I look at the p-values in my regression output, select the p-value which is highest, and obviously the p-value has to be greater than alpha for it to be removed. I remove that, then I recreate the model. In step 3, I remove another variable, so it is all variables removed minus 2, and I keep on doing it all variables for n number of steps until all the remaining variables, so all remaining variables vars are significant. So they all have all the variables remaining in my model have p values which is less than alpha. So in this case, I don't have any more variables left to remove from my model. And this is an automation of the technique that we did over here in our SAS program in our last lecture. So we had started off with all variables in the model. Then I removed race H, then I removed race AA, then I removed social studies. And finally all the remaining variables were significant in my model. And we stopped at that point in time. So that was actually a uh, manual execution of the backward selection procedure. So that was how backward selection works. And the third type of selection that we're going to use is stepwise. So what stepwise does is it's nothing but it combines both backward and forward at the same time. So in forward, we are always adding one variable. So once a variable gets added into the model, it cannot be removed. And for example, when we add in a variable and a few variables later, the original variable that we added in step 1 becomes insignificant, in that case it will not be removed. Similarly, in backward regression, once we exclude a variable, it cannot come back in. And why this happens is that due to the presence of other variables in the model, the p-values don't remain the same, they start changing. So variable once included can again become insignificant, but in forward selection it will not be excluded. In backward regression, a variable once excluded might at some future point in time when we have removed other variables may again become significant. So in that case it cannot come back. So in stepwise what happens is we start off with the variables in my model. We start removing and adding based on the p-values of the variables at that point in time. So in case we want to add a variable or remove a variable, stepwise can handle both. So in most cases people work with the stepwise regression, but there is no such rule. Now automatic selection is typically avoided when we are working with small number of variables, because automatic selection does not look at the business value or interpretation, it only looks at the statistical value. So typically most experienced modelers would want to limit the use of automatic selection, but that said, automatic selection can be very helpful in quickly identifying variables which are significant and should remain in the model, and it can be used to identify the variable set which is important for further investigations. So to show or to cover automatic selection in SAS, we can use the selection equal to option over here, and I'm going to show you backward selection in the HSB2 dataset. So we have the HSB2 dataset, and in the previous lecture I had given an assignment that the student needs to do the one hot encoding and bring in socioeconomic background, school and program as categories. So this is the data set, the procedure to do that. So we had a few extra variables in my data set, so I've actually dropped these variables so we have a cleaner data set, and I've converted all the categoric or nominal variables into binary variables using one hot encoding. So if I look at the HSB2 underscore cat data set, so we have these variables, and on the right hand side we have converted all the categoric variables. So a socioeconomic background had three categories, so I've created two dummy variables, SEB1 and SEB2. School had two categories, so I've created one binary variable for school as well, so it's 0 and 1 depending on it's public or private. And program had three categories, so we've created two dummy variables for program as well. So I'm going to try out automatic variable selection over here. So let's try out forward selection first. And let's have a look. So I'm going to build a regression model, PROC REG data equal to data dot hsb2 underscore cat, so which signifies the categoric variables have been recoded as binary variables. Model math equal to science, read, write, social studies. So that takes care of the subject scores. And then now let's bring in the categoric variables. So gender is one, which is female. Then the other categories that we want to bring in, race. So we've got four races, so we've already created three variables over there. So I'll bring in race underscore H, race underscore A, race underscore AA, which is Hispanic, Asian, and African American. Then we need to bring in socioeconomic background, which is SEB1 and SEB2. So let's look at SEB underscore 1, SEB underscore 2. Then we have school underscore 1. Let's bring that in. School underscore 1. And then we have prog underscore 1 and prog underscore 2. So let's bring in program variable. So program underscore 1, program underscore 2. So these are the variables that we have in our model. And I'm going to apply forward selection. So forward selection is going to start off with the intercept only model in the beginning, and then bring in one variable at a time, starting with the most significant, and continue bringing variables till there are no variables left to add which are significant. So we give the option slash selection equal to forward, and then we have to set the alpha value which determines that what is the cutoff for bringing a variable in. So what should be the minimum p value at which a variable can come in. So that is the SLE criteria, which is SLE, which stands for selection entry. So I can write SL entry equal to, or you can use the SLE also. SLE and SL entry mean the same thing. So I'm going to use the full procedure here, SL entry, and let's put in as a 0.05 as the selection criteria, or alpha equal to 0.05. So we're going to go with p value is 0.05, and that's all. So let's have a look at the VIF also, so in case there is any collinear variable which we may want to remove later on. And that's all I need to do. So press run, and yeah, ODS HTML. I'm going to save this, and I'm going to run this procedure, and let's look at the log. Yeah, so log is run, so we have a model out, and let's look at the forward selection output. There we have it. So this is what the forward selection output will look like. So forward selection step 1, right? When we start off, we have only the with the first step is with the intercept we bring in the variable which is the most significant. So in the step 1 you will see that we have an R square of 0.4386, and the only variable which has entered is read. So read is the most significant variable, and that's entered into our model. Now if I look at step 2, so we'll get step 2. So variable entered, so variable write has entered, and our R square has jumped up from 0.43 to 0.51. And the next variable that has entered is the write, and that's the next most significant variable. Then let's look on ahead. Then I see variable science has entered, and R square has jumped up to 0.5546. So previous R square was 0.51, and now it's jumped up to 0.55. And we have three variables in our model, right? The next most significant variable which has entered is prog2, program underscore 2, and our R square has jumped up from 55 to 58. So we have four variables in our model. Step 5, race underscore A, or race, or the Asian race has entered, and our R square has reached 0.59, almost 60%. So now I now have 1, 2, 3, 4, 5. 5 variables in my model, right? Then it says no other variable met these 0.05 significance level for entry into the model, and this is what the graph looks like. So I started off with an R square of 43, and then you can see the first jump was from 43 it went up to 51, a jump of 0.07. From 0.51 it went up to 0.55, a jump of 0.03. Then from 0.55 it jumped up to 0.58, it jumped up 0.03 again, and then finally it hardly changed a little, and race AA entered, and this was the increase in R square. And beyond that there is no significant variable left, and even our race underscore A is just squeaking in with the p-value of 0.03. So it's almost insignificant. That's the reason, the R square has stopped changing. So if I had a alpha level of 0.01, the forward selection would have stopped at point number 4 itself. So what happens if I change alpha from 0.05 to 0.10? If I do that, I can expect any variable which is lying or which didn't enter but the p-value was between 0.05 and 0.10 will enter in now. So let's try and see if uh, changing it to 0.10 will matter to us. I run this, I look at the final selection, and I see in the final table, I see that in the final table no other variable at 10% is significant, so I didn't enter anything. So let me change it to, let's say, 0.5 instead of this 10%. I'll change it to 50%, and let's see if we manage to squeak in another variable or not. And it goes up to 7 steps, so we have some extra variables. But you will observe that by changing this to 50%, it actually would not change our model performance at all. So if we look at this now, we've checked it and it's run till all variables which p-value less than 0.5 have been forced into the model. And what you will observe is that these extra variables that have been brought in, they have literally not changed our R square. So R square only went up very, very minutely by forcing these variables. So we've entered social studies and female, but from a R square of 0.5991, it has only jumped up to 0.6027, a almost minuscule 0.0023 and 0.0013. So total 0.0039 or 36 is the total extra R square we managed to eke out by forcing two extra variables into a procedure. And that, even if you look at the p-value of the ANOVA for each of these variables, we know these variables are highly insignificant. So we need to actually stop at step 5 itself. So I'm going to go back and change it to 0.05, and that's going to be our final model. So we'll leave alpha at 0.05. So we've got enough variables, so we don't need to worry about changing the value of alpha. So one only tinkers with the value of alpha beyond 0.05 when we are faced with a model which does not have a very high performing R square. So right now 60% of the variance explained, I would say, is a fairly good model. But again, I use that with a pinch of salt. So there's no such thing as good and bad. So R square by itself is not a goal that we need to solve for. It's always the business value of the model. So here we have 5 variables, and this is the final PROC REG procedure, right? The p-value, the R square, and the final model. So all variables that we've entered are significant, and there's no variance inflation. And this was done in one step by using forward regression methodology, all automatically, and the final step in PROC REG using forward selection has given us a model with which we can work with. Now let's try out backward selection. So this was forward selection. I'm going to try out backward selection now. So as I mentioned, in backward selection, we work with we start in the initial step that we go off. We start with all the variables in the model already. So when I change this from selection equal to backward, I have to give in one more parameter, which is the p-value. So SL entry is only, or it's used when variables are entering the model. Now when I do backward selection, variables are only going to be chucked out, or variables are only going to exit the model. So no variable is going to enter the model after it's been removed. So we have another option over here, which is SLSTAY. So this tells us what is the p-value for the variables to remain. So if the p-value of the variables is less than 0.05, then it will not be ejected. So it will continue ejecting one variable at a time till the time all variables in my final model have p-values less than 0.05. So it's the exact opposite of forward selection. So let's run this procedure. I press F3 and let's open backward selection, and let's see how many steps it has run out to. So it's run out to a whole lot of steps. So let's see, let's have a look at that. So these are starting procedure, backward selection. So we have our model over here. So this is the full model with all the variables over here. Let's have a look at the p-value. So which is the highest p-value? 45, no, 68 is higher. Anything higher than 68? There we have 0.92. 0.92. Is there anything higher than 0.92? So there's nothing higher than 0.92. So SEB, socioeconomic background underscore 1, looks like to be the most insignificant variable, and you can actually see the standard error of the estimate is actually larger than the estimate itself. So this variable is pretty much useless in our regression model. And what is the total R square that we are getting? The total R square we are getting with all variables in the model is 0.6038. And the first step, we're going to be removing variable SEB1. So let's have a look. There we have it. No surprise, variable SEB1 removed. And let's have a look at the next model that we've generated. Now, please remember, as soon as you remove or add a variable, the p-values change automatically. So the next p-values of the model, the variable p-values, are not going to be exactly the same. They're going to be slightly different from each other. Sorry, slightly different from the previous p-value that we generated. So we need to look at the table again. And this is the table after SEB1 has been removed. Let's identify the p-value which is the most useless now. And we have a contender at PROC 1. So PROC 1 has 84.84. Is there any other variable which is more insignificant? No. So PROC 1 is the most useless variable right now. And the R square that we got by removing the previous variable was 0.6038. Let's remove this. The backward elimination, PROC 1 removed, R square became from 0.6038 to 0.6037. Hardly any impact. And let's look at the p-values once more. So now school 1 looks to be the next variable in line to be kicked out. And yep, school 1 is removed. And I'm just quickly going to scroll on. Then next variable is SCB2 removed. And then the next variable that removes is race underscore h. And we keep on doing this till the time we hit that all variables left in the model are significant at 5% level. And this is a summary of backward elimination. So we started off with SEB1, then PROC 1 was removed. So this tells us the table that what were the variables removed and in what order, and what was the p-value at which they got chucked out. And this is my final model. So we have an R square of 0.5991, and the variance inflation tells us no variables are significant. This is the variables that we are left with. And so one more word of caution: there's no guarantee that using backward elimination or forward elimination, forward selection, we'll end up with the exact same model. So in this case, we seem to have the same model, but when we work with large data sets, due to interactions and varying p-values at different combinations of regression model, there's no guarantee that backward and forward will give you the same model. In fact, in most cases, they will give you slightly different models. So this was a case where we've employed backward selection procedure. And finally, we're going to talk about stepwise. So stepwise, as I mentioned earlier, is going to use both backward and forward. So one big drawback of backward and forward is that it goes into only one direction in each of those cases. So if you're using forward selection, once a variable has entered the model, it will never exit, even if it becomes insignificant later. And backward selection is the exact opposite. So once a variable has been chucked out, it can never come back, even if it becomes significant later on. So to combine the best characteristics of both backward and forward, and to fix this problem of variables which may become significant later on or insignificant, so I'm going to use selection equal to stepwise. Now, since in stepwise variables can enter and exit at any point in time, we need to give both the SLSTAY and SLENTRY options. So let's give both SLENTRY and SLSTAY at 0.05. Now, one particular caution that we must give is that the values of SLSTAY and SLENTRY, while they can be exactly the same in SAS, in some of the other tools they might give an error that you have to give different values. Now that makes sense. If the entry barrier is 0.05, then the stay barrier has to be higher than the entry barrier, or exactly the same. So you can't have SLSTAY at 0.04. So what you're essentially saying is, to enter the model, the p-value should be lower than 0.05. And SLSTAY says that we will only keep those variables which are less than 0.04 into the model. So that shouldn't be this. SLSTAY can be higher than SLENTRY. So I can have an SLSTAY as 0.10, and that would make sense, because to enter the model you have to be at least 0.05. But once you enter the model, you can stay in, but anything greater than p-value of 0.10 will get chucked out. So you can have SLSTAY which is slightly higher than SLENTRY, but SLENTRY cannot be higher than SLSTAY, so that will create an error. So let's give both SLSTAY and SLENTRY at 0.05, and let's look at the result. So I don't expect, at least in this data set, to have any different results. So selection equal to stepwise is going to practically give us the same result. And this is the stepwise procedure. So we started off. So step 1, the variable started entering. So it starts off with forward stepwise, and they keep on entering, right? And no other variables are left for either removal, etc. So if I look at the summary, only variables have entered, no variable has removed. So you look at the column for removal, no variable has removed, and we've ended up with a final model, which practically is a copy of the forward procedure itself. So in this particular case, no variable was removed, and in fact, I see one interesting nugget. So let me just check. So this is the model that we got using stepwise. Yeah, so my Excel sometimes gets hanged. Okay, I don't need the solver for now. Close, remove. Yeah, sorry about that. So this is my stepwise model. So match destination formatting. So this is the stepwise model that I've got. I'm going to compare this with the model I can get from backward regression. So let's have a look at, sorry, so this was my backward elimination formula. So this is the model which I got using backward regression. And let's look at this. And this is backward. And finally, I'm going to look at the forward selection model that we generated. And this is the forward selection model. So as you can see, in this particular example, all three procedures have given us the exact same model. And once the variables are the same, the estimates, etc., they will be the same. You can't have two different estimates if in the same set of variables. So the beta estimates are also the same, and we have ended up with practically the same model in all three procedures. The only thing is we didn't have to do it manually, but there's never a guarantee that you will get the same model. Otherwise, you won't have these different methods. So this was how to do automatic variable selection using the PROC REG procedure in SAS. In my later lectures, I will cover all of these topics that we've been doing in SAS in the other tools, namely SPSS and Statistica as well, and also how to do it on R. But for now, we will lay out the foundations of linear regression using SAS, and then move on to the other tools. So in this particular lecture, we wanted to cover automatic variable selections and the three procedures, namely forward, backward, and stepwise. So in the syntax, we've covered the selection equal to option for backward, forward, and stepwise, as well as the SLSTAY and SLENTRY parameters in which we give the cutoff of the p-values. So you can use SLS as a shortcut, or you can use SLSTAY. Same for SLE or SLENTRY, it doesn't matter. However, we've already covered that SLENTRY cannot be higher than SLSTAY. Alright, so I'll see you in the next video, and we will talk a little bit about overfitting in our next video.